Well, welcome back to our class on system engineering. Unfortunately, this is the last lecture that we'll have in this class. And this is the last lecture in this third section that we have, where we have these supplemental topics, which really are trying to give some greater insight into how we go about doing system engineering and where it has a lot of value. And especially this last chapter, we're going to be having a relatively short chapter showing just some of the key things why system engineering is a very important thing to include. So this chapter will be exploring the value of system engineering, and there'll be 6 things that we'll focus on. Problem and solution discovery. That's something that we can be doing in system engineering. Communication, making sure that things are effectively communicated through all the important parties. Identification and solution of the showstoppers as early as possible. Error reduction of both product and design systems. Risk reduction of both the product and the design system. And finally, continuous improvements of the system design. So we'll handle these one at a time. And so in terms of saying some of the key metrics that can start to play out here is with system engineering, there can be better technical leadership. So better technical leadership corresponds to program success. Better or more system engineering correlates to shorter schedules, more and even in the face of greater complexity. Better and more system engineering correlates to lower development costs, say by 30% or more. Optimum level of system engineering is about 15% of the total development program cost. So that's an important number to remember if someone are trying to estimate, well, how much should be allocated for system engineering. Programs typically allocate about 6% of the total development cost to system engineering. You can see this is less than half of what the recommended value is. And so it's like, using the analogy I've mentioned, this is like being underinsured. And so maybe in some of the cases it would be fine, but there may be some times where cutting things here, it's going to cause some greater problems down the road and cause a lot of costs that would end up being realized. So in terms of research result, positive statistical relationship exists between system engineering activities and the 3 measures of system engineering success: cost compliance, schedule compliance, and overall stakeholder success. So the optimal system engineering effort is between 14 and 15%. And so here we're showing an example. There's a reference. You can look that up in the textbook. The characteristics about a program that are most relevant to determine the amount of system engineering to consume are level of problem definition at the start of the program, autonomy of the development team, the level of the integration needed at the system level, the size of the system, the difficulty associated with proving the system as the appropriate system, and the risk associated with the technologies being integrated into the system. And there is significant positive return on investment for system engineering activities. So it's estimated somewhere between 3.5 and 7 to 1. Here are some summary of system engineering and a summary of systems and software engineering successes and failures. So for the UK Ministry of Defence, the top 25 programs slip 35 to 40 months on average. 10% of the project missed key technical requirements. The UK information technology, 10 to 20% met successful criteria, 40–50% laid over budget or did not meet the technical goals, and 40% were failed or were abandoned. And for the US information technology, 16% projects success, 43% projects challenged, and 31% projects canceled. So you can see that there's a lot of room for improvement if we don't have the right level of system engineering and software engineering. So we talked about these things, the value of system engineering. So here's another listing: the problem and solution discovery. So this is in the goal-seeking system, in the beginning and the formulation of a program, being the communication interface between the stakeholders and the design engineers. You'd be surprised how so often that communication can break down, and that can cause some huge negative factors in a program. System engineering is helpful in the identification and solving of program stoppers, avoiding failures due to operation considerations, avoiding failures in the product system, and minimize unintended interactions of both products and design systems. They're actively involved in the error reduction of both the design and the product system, risk reduction of both the design and the product system, and continuous improvements of the system design. That's in the area of enhancing both process and content and increasing productivity and effectiveness. So for problem and solution discovery, there's a two-level discovery problem. What is a problem and what is an acceptable solution? So you have to know what the problem is before you can come up with a solution. And the solution takes the form of a hierarchical set of specs and interface control requirements. Control documents. And so all of these things need to be done. And this is compounded by the discovery qualification system and concurrent systems. And so there's just a lot of moving parts that need to be walked through when you're in the problem and solution discovery part of a program. So for the types of goal-seeking system, high quality, you want to be looking for high quality for defined products and high probability of success for undefined products. The types of discovery focus can deal with discovering the problem to be solved, discovering the solution that is the right balance among stakeholders across the life cycle and across the engineering disciplines, and adding value based on systematic considerations. Here's a comparison of the traditional requirements and goal-based approach. So we have a traditional where you go from the scenarios, functions, outputs, performance, concept generation, steady state concept, and the design. And so with a goal base is you want to be focusing on, well, what does the user need to have goal definitions, work on concept generation, research and development. Then you have the concept and evaluation, and have the user acceptability milestone review here. And so more of a focus on the user from that point of view. So what are, quote, sidewinders? Use of goals. The use of goals precludes change in requirements. The use of goals coupled with continual customer interaction works to prevent customer dissatisfaction. The use of goals results in the system that meets user needs. So you can see that you're focusing on the goals. You're closely collaborating with the stakeholders and the customer. The use of goals precludes the adherence to formal specification, thus allowing for early and rapid testing. The use of goals supports experimentation, encourages the best solution to technical problems to surface. The use of goals does not constrain system design. So now we get into system engineering as a communication interface. The stakeholders and the design engineers do not speak the same language, or more correctly, the same dialect of the common language. And so there has to be that translation. There's often a great diversity of opinion and some diversity of language among the non-homogeneous groups of stakeholders. Similarly, there's often an equally great diversity of opinion and even greater diversity of language among the non-homogeneous groups of design engineers. The folks that are working on a control system are going to be different from those working on a battery or whatever types of things that you might be considering. So you want to be gaining closure with the stakeholders. We'll talk about that first. So determining the needs assessment and gaining agreement on a path forward. And so it's going to take time and effort, and the system engineering team is going to be key for doing that. So first, we're focusing on the gaining closure with the stakeholders. And then next, as we're working on the gaining closure with the design engineers. So you want to be including representations from the beginning so that they have buy-in and they have understanding of what is actually going on with the design development. You want to document the decisions for derived requirements. they're going to know how to do things better than the system engineering team. And the system engineer needs to relay that back to the customer. So there's going to be going back and forth between the stakeholders and the design engineers. And you're going to need to codify those findings for each one of those. System engineering is very useful to avert showstoppers. So system engineers should test for and find showstoppers. It could be anywhere: problem understanding, the solution definition, the problem resolution system, the test system, and it just goes on and on and on. And so you can be thinking of a variety of different systems that's been out there and that were designed well, and maybe it turns out that the market wasn't there when they designed it. Iridium, there's a lot of different examples. Personally, I have some awareness of that there was a lot of churn that the industry had predicted that there was going to be a huge need for this kind of a service. And at that time, when Iridium first came out, it just flopped and it went into bankruptcy and never quite had the market that it wanted. And so why wasn't this found early to say that, you know, the market's not quite there, the technical areas, the amount of cost that it's going to take versus the market, they don't match. It turns out now, and we're talking like 20 plus years later, there appears to be more of an appetite for this kind of proliferated LEO constellation, low Earth orbit communication architectures. And here's just another chart talking about the Iridium communication satellite system. And so it was talk to anyone, anytime, anywhere, from anywhere. And unfortunately, no one asked the obvious question. And so the handheld phones were busy. The cost per minute was expensive, and so it was just a huge expense. And then the market never realized it. That the gleam that everybody had in their eye when they were first conceiving it. So what about system engineering to find and fix errors? So what are some examples of the sources of errors? Not looking for errors in associated signals, ignoring signals, looking for but missing signals, and misreading signals. So those are examples of where things could start to come out and show themselves as being a concern. For types of errors, there could be requirements changes. All of a sudden, a new requirement is put on board and it wasn't analyzed well enough to know what the impact is. There can be engineering design changes. And so things can be misinterpreted and maybe the waiver is granted where it doesn't fit. Or things are completely missed when things there's engineering design changes and there's a ripple effect. There can be test issues. Something may not be tested properly. That things are actually not caught in testing, or there's misinterpretation of what actually the data is telling you, and it just goes on and on and on. So here are examples of the types of areas that should be discovered as early as possible. New requirements or goals that are missed, changes in requirements or goals, changes in derived requirements, engineering design changes that are not communicated properly, engineering design changes that should have been made, engineering design changes that were communicated properly but were being misinterpreted, tests that are not being performed, tests that are being done incorrectly, tests that are recorded incorrectly, tests that are misinterpreted, tests that are beyond the point that is necessary, and not performing regression testing properly to the extent needed when something takes place, a concern or an error or a fault. So here is a general taxonomy of the sources of errors: not looking for errors that exist, looking for errors but not looking for all the signals, ignoring signals of errors, looking for signals of errors but missing them, and misreading the signals associated with the errors. And so those are a taxonomy of things that you might want to keep in mind. Risk mitigation is a very important area in terms of there are going to be things that are possible that could really have a huge detrimental impact on a program. And so they need to be quantified, and there needs to be a mitigation plan put in action. And so this is what we have here is we have a 5x5 matrix, which is typically how you start to point out where a risk would be, and then you would have it labeled here. And so we just have each of these squares labeled, but say you have a risk that lands way up here, where it's a high consequence and a high likelihood. That would be something that you would really need to work on. So it's a high risk, and so you want to have a complex risk mitigation to start to push that down into a better area. So in general, the risk management activity is trying to push it down from this all red area where it's a high risk down to this low area where it's a low consequence and a low likelihood. 5 common core risks to be looked for are wishful thinking about the number of problems. And so you really needed to quantify these. The requirements are specification failure. This can be dealing with an inability to achieve consensus among stakeholders. Scope creep, too many requirements were missing at the beginning and show up before the system is completed. And this can be a huge problem. Loss of key personnel, which can cause many other risks. And finally, productivity variability of the system engineering system, which leads to schedule problems. So for continuous improvements, you want to be monitoring the substance of the design, work in the context of the whole life cycle. You want to be leveraging, say, the use of design patterns. Is there an effective use of a design that has been done before? Does something need to be codified so it can be captured for future designs? And also continually examine the product platforms and how are they performing. You want to be utilizing various methods, tools, and techniques associated with the design. So this is the last chart. And just as a reminder, the system engineering provides 6 main values to program and project management and funding agencies. Goal-seeking system driven towards the stakeholders' goals. The communication interface with the stakeholders and design engineers so that each group can affect the objectives and constraints of the other. Means to find showstoppers early and avert them. And error discovery and resolution so that the errors are fixed when the fixes are inexpensive, and risk management that identifies and finds risk mitigation solution, seeking cost-effective approaches. And finally, system engineering is helpful in being involved in the continuous process improvement of everything that's being done. All right, well, thank you very much. This is the end of the lecture, and this is the last lecture that we'll have in this course. So thank you very much.